Based on the derived equations of motion, we found two key natural frequencies for the system. The two theoretical natural frequencies were determined using MATLAB. The frequency for x in the first row and the natural frequency in the second row for theta are shown in the following equations. Omega x describes linear translation of the cable car as a whole, while omega theta describes the rotation of the cable car. For the sake of this project, the simulation of this system was simplified by considering the cable as a discrete rather than a continuous system. However, in real-world scenarios, omega x will require additional information such as tension of the cable supporting the cable car, Young's modulus, and the second moment of area. In addition, the initial conditions of the cable were assumed to be a pin-to-pin connection. ANSYS Workbench was the software of choice to perform this simulation. Boundary conditions were applied using the static structural solver. The spring base was constrained as a fixed support, and the frame was fixed in the z-axis with degrees of freedom in the x and y-axis. The first two mode shapes of the model that were considered moved in the longitudinal and transverse direction of the beam. This allowed the application of small angular approximations to this 2-degree of freedom system. The simulation was done for two spring cases. The stiffnesses for each case were 367 and 706 newtons per meter respectively. The fundamental frequencies from modal analysis were consistent with the findings from MATLAB. As shown, Mode 1 and Mode 2 are the most significant because they are most likely to occur due to the loading and movement of passengers. Mode 3, 4, and subsequent modes occur due to external or environmental factors, for example wind, which affects the pitch and yaw of the cable car as well as slight precession. From this experiment, the occurrence of the cable car exhibiting higher modes before reaching resonance is highly improbable, and does not have a significant impact on the system. Harmonic analysis was used to evaluate the velocity of the pendulum. In the range of 1 to 90 Hz, the ANSYS simulations show that the velocity of the cable car was highest when a natural frequency was applied. This can be observed from the peaks shown. The velocity peaks out at Mode 2, causing the pendulum to sway vigorously. Therefore, this natural frequency is generally avoided, and the maximum wind speed of the chassis, v, is directly proportional to frequency and wavelength, where the excited frequency must be less than the natural frequency.